This is also a lever. Gear lever also is a lever. This is a bell crank lever. Yeah, it looks like this. Bell crank lever. This is a lever safety valve. This is a model of lever safety valve. This is above the boiler drum. You can see this is the boiler drum. This is a pipe above the boiler. This is a valve seat. This one. Valve is connected to the lever. Here it is the fulcrum, and it is here is the weight. Dear students, welcome to another day's lecture on elements of machine design. Today we will see foot lever. We have seen the design procedure for designing hand lever in yesterday's class. So now today let us see the foot lever. See, foot lever, it is shown in the figure like this. See here. See, this is much similar to the hand lever. This also, you see, the shaft is there. This is the shaft, you see, and it is shaft is fixed in a bearing. Here only one bearing is shown. Normally, any shaft will be mounted on two bearings. Bearing means support. Okay, there are two supports. You see, it should be two supports. Actually, we have broken it here. There may be another support. Okay, so this is the shaft. On the shaft, this boss or the hub, you can say, or boss, you can say, of the lever is fixed, and this lever rod, you know, that is nab, see, tapering along the width, but thickness is uniform. You can see thickness. You can see in the top view, or what, in the front view. Yeah, this is the top view. You can see in the top view, you can see the thickness, and in the front view you can see the width. Width is tapering. So why it is like that? Because the maximum bending moment is, you see, as from the application of the effort, the further you move, the more will be the bending moment. The more the length, more bending moment. So it will break at this point. That's why where it will break, you keep the maximum bending moment. and in the other places it is not necessary. It's a wastage of material. If you are taking a rectangle like this, if you are taking a rectangle like this, it's a waste of material. Okay, so that's why it is provided in table. Okay, this is the lever rod, and here instead of the handle a foot plate is provided. You see, this is where we apply our with the help of foot. With the help of foot we apply the effort. Okay, this is the foot lever. So what is written here? The foot lever uh, is designed and designated in the same way as the hand lever. The only difference is that the handle is replaced by the foot plate. Here there was a handle in the hand lever. Now that is replaced by a foot plate. The force exerted by a single person by foot is taken to be 600 newtons to 800 newtons. You see, last time I told, with the hand, what is the average load that you can lift or you can apply? That is considered to be 300 newtons or 30 kgs. Okay, so with the foot how much you can apply? 600 newtons, double the amount. If you can weigh, if you can apply a force of 30 kgs with the hand, or 300 newtons with the hand, you can apply with the leg 60 kg or 600 newtons, like that. 600 to 800. If he's a very strong man, you can exert 800 newtons, like that. Okay, so let us see. Now we will directly go to a problem instead of design procedure. So because it is much similar to the handbrake, handle lever, sorry. The foot lever, this is asked in summer 10, summer 2013. Okay, the foot lever is 1 meter long. When we are saying 1 meter long, this L will be 1 meter long. Okay, and from the center of the shaft is this one, to the point of application of load. Application of load is P. So this distance L is 1 meter. 1 meter means what? 1000 mm. We always, in every formula, we should not put in meters and other things. We should bring to millimeters, and you will not face confusion. Convert everything into millimeters. Okay, and the application of 800 Newton load. See, I said it is from 600 to 800, so this must be a very fat man. And with a big, with a heavy foot, he is applying a load of 800 newtons, that is 80 kg. Okay, now what they are asking, find the diameter of the shaft. Anyway, this is the first step that we do, finding the diameter of the shaft. Then dimensions of the key. Dimensions of the key, last time we omitted because we are going to see this in the chapter of shafts and keys and couplings. Okay, in that chapter we'll see. Here also we will omit. Okay, then next, then the dimensions of the rectangular arm. This is the rectangular arm. How is it rectangular? If you cut it across, the cross section is rectangle. That's why it is called as rectangular. It could have been circular, it could have been elliptical, anything. Okay, rectangular arm of the foot lever at 60 mm from the center of the shaft. From the center of the shaft, 60 mm. So at a distance of 60 mm, assuming it to be about the periphery of the hub there, hub circle there. Center of the shaft, assuming the width of arm is 3 times thickness. You see, now we are having something called as B. Okay, and something as W, or this can be this could have been T, and this could have been W, or width and thickness. Okay, this width no, this width is more compared to this thickness. So what is the ratio of width to thickness? That they have given. The width to thickness ratio is 3. So if one of the things, if you find, the other you from this you can get W upon T is 3 times. Okay, then allowable tensile stress may be taken as 73 Newton per mm square, and shear stress is taken as 70 Newton per mm square. Okay, now come, let us solve the problem. So the length is 1 meter, that is 1000 millimeters. The overhang is 60. How do we know it is 60? Is it anywhere given? The dimensions of rectangular arm of foot lever at 60 mm from the center of the shaft. Oh, see, that 60 is not this 60. That 60 is this. Dimensions of rectangular arm. This overhang, that is x, that is 60. Overhang length is 60. Okay, then b is the width and t is the thickness. So please don't confuse. This is not b, this is t, then this is b, this is b, and this is t. Like that it is. Okay. So load is 800 newtons. Shear stress is given 70, and tensile stress is given as 73. Okay. Now first let us calculate. You see, this is the equation that you have to use to find the diameter of the shaft. First step is finding the diameter of the shaft. Before that, you should know what is T, because T is directly not given. We only know the effort that the foot is applying, and foot is applying at a distance of 1000. Foot is up for, that means the effort into the distance, that gives the twisting moment torque. So T, this formula you should use, P into L. So that is 800 into 10 cube Newton millimeters. This also you should always keep in millimeters. Don't put in meters. If you are keeping in meters, somewhere you will commit mistake and it will go wrong. Okay. Next. So once you know this, only this is unknown. From this, no, you find out T is got here, and you will find it is 38.75. As I told you before, 38.75 rod you cannot get. So round figure you have to make it. 39 also you won't get. So this is the standard value, 40 mm. So D is 40 mm. This is the final value of the diameter of the shaft. Diameter of the shaft means what? See, this is the diameter of the shaft here, D. That is what we have found out. Okay. Okay, the diameter is 40 mm. Next is diameter of the shaft in bending. You uh, see, not only torque, bending also is coming. So torque is P into L, that is 8, that we have already calculated here. And bending moment is P into small l. Why? Because of this overhang here. You see the bearing is here. The overhang is this. Okay. See, if it is applying, force is applied at this point, no, there won't be bending moment. But you are coming to the side and then applying force here. Here applying means what? Here means, it is on this line only. Here we are applying. That means, because this is so much of overhang is there. That means, this is like a cantilever and you are applying force like this. So because of that, what? A bending moment comes. So that bending moment is this, whatever is this load P, that is 800, which is being applied here on this line here, and this distance L. It is taken as X here. There they are saying L. So don't worry about the notations. Only you should understand what it is exactly. Okay, P into L, that is 800 to 60. This becomes the bending moment. So once the twisting moment and bending moment both are got, you have to find out the equivalent twisting moment or the equivalent torque. That is square root of m square plus t square. So put these values here, this and this. Okay, and then you will get equivalent torque here, this much. So once this is got, then you can find out what is now what are you doing. You see, first we have found out the diameter of the shaft here. Now the diameter of the enlarged portion of the shaft in the bearing, okay, at the middle of the bearing, that's what we are finding out now. That is what? That is D1, is it not? D1. This D1 is being found out. For that, we are considering the equivalent twisting moment, and the same formula, that is um, uh, torque equivalent is equal to pi by 16 tau d cube. That is the formula we are using here. You put all the values, you don't only not having d1, so you will find d1. This is again 40. You see here, d also we have got 40 only. The 40, the enlarged portion means it should have been bigger than that, but this also we are getting 40 only. Okay, that means what? Even if you don't reduce the diameter, it is okay. That is the meaning. Okay, that means this entire this length can be of the same diameter. From this diameter as well as this can be same, means there is no step here. Here actually step is there, no, like this and like this and like this. So that step need not be there. It is can be straight also. But anyway, see, for locating of boss and other things, a minute step of half a millimeter or 1 millimeter is provided. Okay, so like that. So now we have got d and d1. So after d1 is got, diameter of the boss db and length of the boss db, lb, these two can be found out with the empirical relations. These are the empirical relations, and then we have to find out, okay, you see, now we have found out this small d and this d1. These two we found out. After finding out this lb and this db, that is the diameter of the boss and the length of the boss, these things with the empirical relations we found out. And then now this thickness t and this breadth b, these are the two things remaining. So for that, now they fail. The lever fails in bending only. So bending you have to consider. So lever fails in bending. The lever is subjected to bending due to force applied at the end of the lever. Bending moment is, you see, I told you bending moment is maximum where at this place. Okay, what is the distance from here to here? See, this is the L minus of this. Minus of this means dB by 2. That is the meaning. Okay, so that is the bending moment. So bending moment is equal to load into L minus dB by 2. Okay, so dB we have already calculated here 64, so this will be 32. Okay, so you will get bending moment, and this is the section modulus. Why section modulus? Because sigma b is equal to bending moment upon section modulus. Bending moment is this value. This is again, you see, be careful, this is Newton millimeter, not Newton meter. Okay, so section modulus is 1 upon 6 TB square. BT square or TB square? It is TB square. Why TB square? Because thickness is smaller, breadth is larger. Larger will have the square. Okay, so 1 upon 6 TB square. Okay, that values, and the relation between t and b, because there will be two unknowns here. T also is unknown, b also is known, but we have, in the formula itself it is given b is 3 times of t. So you replace that. Okay, and you will get t is 19.19 came, so round it to 20, and the width will be 60. This is how you finish the design of the foot lever. Okay, now come to the design of bell crank lever. This is the design of two arm lever. Bell crank lever is a two arm lever which are right angles to each other. You see, right angles. You see, this is the bell crank lever. Bell crank lever, see, this axis, they are 90 degrees. So these two arms are at right angles. The bell crank lever is used in railway signaling. I told you in the few years back they were using these things in the railway signaling. Then governors also, Hartnell and Wilson, Hartnell governor, etc. The design of the bell crank lever includes to find the dimensions of 1. Fulcrum pin, boss of the lever, and cross section dimensions of the lever. Cross section dimensions of the lever means just now how we found out the levers dimensions, considering the bending failure. Okay, bending stress. So boss of the lever and fulcrum pin. So these are the things we had found out. You see here. You see, this is the longer arm. Longer arm is the effort. Effort means, whichever we are applying with the help of hand or foot or what. Okay, and this is the weight. Okay, this is a shorter arm. Okay, the length of the weight, length of the effort. Okay, and here there is a fulcrum. This is the fulcrum. Okay, here also there are pins, why? To connect with some other links. With nuts, bolts, you can connect. Okay, or pins you can connect. Okay, so you see it is like this. So we have to design this. See, this diameter inside is d1. See, outside diameter is do. Okay, and these things, the dimensions of these things we have to find out. Okay, come. So the design procedure for bell crank lever is as follows. Determination of the load as per the problem. First you have to see, you have to find out the load. See, let W be the load. This is the load W. Okay, and P is the effort. It is the P on the other arm. Okay, and LW is the arm length, and LE is the see, load arm length, and LE is the effort arm length. Okay, so to find out what is W, what you have to do, you have to take bending moments. You see, bending moments. You see, this is the fulcrum. Okay, and this load is causing a moment in the clockwise direction. This load is causing a moment in the anti-clockwise direction. So this W into LW should be equal to P into LP. That is the moment. Okay, so W into LW, P into LE. E means effort. Okay, like that. So from this you have to find out the load W. Once you have found out W, you have to find out, see, this this load is acting this direction, this load is acting that direction. That means, this will be, both are pushing, not this. Okay, both are, it will push in this way. To for equilibrium sake, what should be there? There should be a reaction in this direction, which is called as, which is referred as R. R means what? RF, reaction at the fulcrum. You see, this is the reaction at the fulcrum. This reaction of the fulcrum with the, you can find out the resultant. You see, you must have studied in applied mechanics or some materials how to find out. So this is the formula we use because it is 90-degree angle. So it simplifies to square root of W square upon P square. So this you will find out reaction at the fulcrum, or the resultant force that is acting at the fulcrum, RF. So that means what? Here in this place, what load is coming is RF. It is not W or P, because they are acting at some distances. So what exactly is working here? That is RF. Okay. Now, design of the pin. Pin means at the fulcrum. That means, that is there here inside. Okay. So that cylindrical piece is called as a pin. That is what we are designing. Yeah. The fulcrum pin supports the lever and allows to oscillate due to the relative motion of the lever on pin. Fulcrum pin is subjected to bearing pressure and direct shear stress. You see, there are, actually the bell crank lever is moving about that. So we have studied something called as bearing pressure. You remember when we studied about what is that, crushing stress and bearing pressure. Crushing stress, bearing pressure, both are, localized compressive stresses, Crushing stress was when there is no relative moment. Bearing pressure is when there is relative moment. They here know that about the pin, this lever will be oscillating. That's why here bearing pressure comes. Bearing pressure is given by capital P suffix B. And also direct shear stress comes upon this pin. We are talking about the pin. We are not talking about the lever now. Okay. So now fulcrum pin is designed by considering under bearing pressure. You see, bearing pressure, what is the load coming? RF is coming. And what is the area? See, whenever bearing pressure comes, we have to take the projected area. Projected area is LP into DP. You see, in this, come to this figure back again. Only that we didn't show top view in this. You see, here a pin is there. That pin, is it the size of D1? No, it is little bit smaller, because on the pin, on this pin we will put another bush. Okay, the bush may be 1 or 2 centimeters, 1 or 2 millimeters thick. Okay, so that means what? See, there are two circles here, and after that one more circle will come. Why one more circle? That is the diameter of the pin, and between the third circle and the second circle, what is there will be push. Okay, and in the top view, if you see, it will look like a rectangle. So that is the length of the pin. Okay, that is the radius, that is the area, length of the pin into diameter of the pin. Okay, and this is an empirical relation we are assuming. That is, length will be 1.25 times of the diameter of the pin. Okay, because there is only one equation, no? Wow, and two unknowns are there, we cannot find out. So PB, this PB should be given in the problem, and RF we have calculated, and this, no, now it has become only one unknown because of this relation. So now from here you can find out what is LP and what is DP. And afterwards, after bearing pressure, something else also comes upon the bearing pin. What is that? Direct shear. Direct shear means what? You see, if this reaction force is so much, the pin that is there may cut on either this side and that side. So it may shear off in double shear. So double shear here, direct shear, double shear. That's why this area is 2A. Okay, so 2A means 2 into cutting in a circle. The circle is pi by 4 dp square. This is the area, 2 times 2 sides, because it is double shear. So this is the formula we are going to use. Tau is equal to RF upon 2A. Okay, and from this, dp is already found out. So therefore, what you will do is, you will find the induced shear stress, tau I, induced shear stress, and compare it with the given shear strength of the material. And if the induced stress is less than the strength of the material, then the design is safe. Okay. Next is diameter of the boss of the lever. You see, I was telling you. You see, then that place, no, if you cut it like this, there are three circles. One circle is for this, which this inside one is our diameter of the pin. Now this one is D1. D1 is the inside diameter of the boss, or outside diameter of the bush. See, this is pin, this is bush, and this is boss. Okay, the spin diameter is dp, and inside diameter is d1. Is it d1 or di? It may be di, because inside you can. Okay, but now for me it is appearing as 1. Okay, because this is O, I'm thinking that it could be I. Okay, inside diameter of the boss, outside diameter of the boss. Inside diameter is the same as the outside diameter of the bush, and inside diameter of the bush is the pin diameter D. Okay, so there is relative motion here. One, the boss of the lever is subjected to bending stress due to the bending moment lever. See, the boss also can be broken there in this section because of the bending moment. See, DO is the outside diameter of the boss of the lever, DI is the inside diameter of the boss of the lever, and LP and LB, that is length of the pin and the length of the boss, are equal. Okay, there is a relative motion between the fulcrum pin and the boss of the lever. See this, yeah. Here this pin, you see, if this boss is oscillating, this pin is stationary, so this is stationary and this is oscillating, means there is relative motion. There is relative motion means what is happening? See, you imagine, see, I am showing you the side view. The front view may be, you know, kind of this is one circle, this is second circle, and the third circle. See, the third circle is rotating over the second circle. Then what will happen? There will be, you know, relative motion. Relative motion means what? If anywhere relative motion is there, there will be friction. If the friction is there, what will happen is, you see, the lever will wear off. Therefore, a bush is provided, a brass bush. It is not plastic bush. It is made of brass. Brass is a metal. Okay, copper alloy. Copper alloy. Okay, brass is copper and zinc alloy, I think. Okay, 2 or 3 thickness should be press fit. Press fit means what? You know, you have to with force insert it into the boss of the fulcrum. Okay, lever as a bearing, so that renewal becomes simple when wear occurs. Wear occurs, wear means what? वो घिसाई घिसाई होता है. घिसाई कब होता है? अगर दो चीजें जो है ना रगड़ते रहेंगे तो घिसाई होता है. अब ये दोनों रगड़ते रहेंगे तो घिसाई होता है, तो ये होल बड़ा हो जाता है. फिर जहां पर फोर्सेस जैसा अप्लाई करना चाहिए वैसा अप्लाई नहीं होते हैं, तो क्या करना चाहिए? बीच में अगर बुश दे दिए तो बुश रगड़ जाएगा, बुश कम हो जाएगा. बुश थोड़ा सॉफ्टर मटेरियल रहता है ना. ये जो है ब्रास का क्यों लेते हैं? क्योंकि ये जो स्टील के जो होते हैं दोनों, ये स्टील से ये सॉफ्ट होता है, तो अगर घिस गया तो सॉफ्टर मटेरियल घिस जाता है, तो इसीलिए बुश को वहां रखते हैं. कुछ दिनों के बाद अगर बुश घिस गया तो उसको निकाल के दूसरा बुश लगा दो, क्योंकि बुश जो है ना सस्ता होता है. ओके, छोटा मटेरियल, छोटा साइज का है, सस्ता मिलता है. Okay, so now inside the diameter of the boss will be diameter of the pin plus 2 times the thickness of the bush. Thickness, you see, on one side 3 on one side 3 the other side 3 means, you know, 2 into 3. Okay, so the inside diameter of the boss will be diameter of the pin plus 2 times of the thickness of the bush, that is 6 2 into 3, 6 You see, if bush is not used, you see, there is no question of bush is not being used. You have to always use bush. So remove this point. Okay, then outside diameter will be, this is an empirical relation, 2 times of the diameter of the pin. Okay, the maximum bending stress induced in the boss, maximum bending stress induced in the boss will be sigma b is equal to m upon z. Z is I by y. I by y. Z. Z is section modulus. Okay. Section modulus I by y. I is 1 upon 12 into LB into DO cube minus DI cube. You know, you should be able to, from this from this rectangle, you should be able to find out the section modulus. This the section modulus I by y, and y, where is y? Oh, y we has taken here, that is 0 by d0 by 2. That this y has gone up, so this m into y divided by I is this. Okay, so now sigma b is equal to, say, this 12 and 2, this you know, results in 6 m do upon lp into do cube minus di cube. Okay, now if you know di do, everything, you know, M you can find out, M is W into LW or P into LP. Any of the two equations you can use and find out what is M. Once you know all this, see what outside diameter boss can be. An outside diameter is already got. You see here we have got outside diameter by this empirical relation. So therefore we are not going to find out outside diameter. We are checking for the bending stress. So this is sigma bi, that is induced bending stress. Sigma bi should be less than the allowable. Allowable means that of the material which is given in the problem. If sigma b is not given, you should take it sigma t. Okay, because sigma t also is direct stress, sigma b also is direct stress. Okay, then next is design of the lever to find out dimensions. Lever from means, you know, where, see the dimensions. Yeah, where is it? Yes, sorry, here. See this width and perpendicular to the paper, the thickness. Okay, that is what we are finding out now. Because it is rectangular in cross section, we know that it fails because of the bending moment. So bending moment is load into the distance from the load to the periphery of that circle of the boss. Okay, that is L minus d0 by 2. You can use either this formula or this formula, because one side effort is being applied, another side load is being applied. Okay, either of these two, both will work out same. So this formula, bending stress is sigma b upon m upon z. From this, section modulus is simply 1 upon 6 tv square. M is, you will get from this, and you can find out what is b and t. Again, no, b and t, two unknowns will be there. Okay, b and t, see, yeah. You see, this z is I by y, the I is 1 upon 12 bh cube, and y is half of the h, that is h by 2. So bh square, 1 by 6 bh square. So bh square, again now two unknowns are there. Therefore, what you have to do is you have to use some empirical relation. What is the relation between b and h? You see, you can use it as you can take it as h or t. It doesn't matter. H means height, T is thickness, like that. Okay, you know, but but the thing is, to which you will put square. Square will be always to the larger of the two. B and H, no. See, if it is TB, then we said TB square. If it is BH, no, then we are BH square, like that. H is 2 times of 2 times of B to 4 times of B. 2 times B, 3 times B, 4 times B, you can use. 3 also, 3 in the middle you can take. Okay, so from this relation, from this equation, no, from this equation, you can find out both B and H. Okay, and sometimes this can be elliptical section also. If it is elliptical section, you know, this formula will be used. This is the moment of inertia for the elliptical section, and for y will be half of the h. Okay, so you will get values like this. Okay, and from this you can find out what is B and what is H. This is B and this is H, and H and B, this relation can be taken as 1 point or 2B to 2.5B. Okay, if you substitute values like this, you will find the dimensions of the lever. Okay, with this we finish bell crank lever. You solve some problems, and if any problem, you refer to me. Okay, we'll stop here. Thank you.